Hello, everyone. We will start at 2:30, but I can start talking before, so we will not just wait and wait and wait. So I will give very brief information about our track. We had 15 papers submitted to the Manycore and Multicore track, and out of these 15 papers, after discussions and scientific committee meeting, 3 best papers were selected for presentation, and we will have 3 presentations during today's session. So these presentations are pre-recorded, and then we will have question and answer session, 5 minutes roughly for questions and answers. Please type your questions to the Slack. I'm not sure if everyone can ask questions from Zoom. So certainly, if you type your question to Slack, I will be able to read it later. And we still have few seconds for starting the session officially. Okay, welcome everyone. The session, the time is 2:30 p.m. So we can start officially the session, and the session will start with presentation of the first paper, NVPhTM, an efficient phase-based transactional system for non-volatile memory, and it will be presented by Alexandro Baldassin from São Paulo. Please start the presentation.
Hello everybody, my name is Alexandro. I'm going to present our work on NVPhTM, an efficient phase-based transactional system for non-volatile memory. This is a joint work with my colleagues from Brazil, Rafael, Murari, João, Carvalho, and Guido, Araujo, and also my colleagues from Portugal, Castro, João, Barreto, and Paulo, Romano. So the motivation for this work is that byte-addressable persistent memory is finally becoming a reality. A major example is Intel Optane C. The good thing about these new memories is that we can issue load and store instructions directly to persistent memory, but it also comes with some issues. So how do I keep my data structure consistent in the presence of failures? Of course, we don't want users, programmers to deal with different logging strategies using low-level flush instructions. So researchers have come with some more high-level approaches to deal with that, mostly based on transactions, and kind of reusing previous work on transactional memory. So the idea is to add durability to transactional memory. We have 2 main types of implementation, let's say. We have those based on software. Examples are NMOS and NVHeaps. And also we have examples that use the hardware approach, mostly based on Intel TSX, such as DoTM and NVPhTM. And of course, we have different trade-offs with these two different ways of implementing. On the hardware side, it's resource constrained, so it's providing the best effort way, so we cannot execute all kinds of transactions. Whereas in the software part, we have this instrumentation overhead because every read and store operation has to be instrumented, which obviously adds overhead. Here I have two examples that illustrate those the different strategies. Two applications from the STEM benchmark. On the left side, I have Labyrinth. So the blue bar is the hardware approach, which I'm just calling NVPhTM. You can see that for the Labyrinth application, it's less efficient than the software approach, which I'm calling just PSTM here, the orange bar. But if you look at the genome, you can see that the performance is very different because here hardware is better than software. Again, we don't want users to choose the best system based on application. The idea is to come up with a system that dynamically detects that and deals with that. If we look back at the literature in the volatile world, we have two main ways to deal with this. One is using hybrid systems, where we allow both hardware and software transactions to execute concurrently, or you can have phase-based systems that allow just one type of transactions to execute in a phase. For instance, if I have a hardware phase, only hardware transactions are allowed to execute in that phase. Well, I won't go into much details about the specifics of each system. I just say that there are some performance issues with hybrid systems, so we decided to focus on phase-based systems. And our contribution is to add durability to a phase-based transactional memory system. This is what NVPhTM is. And there are two main challenges here. One is how to devise the heuristics for transitioning between the different phases in the presence of persistent memory. And how do I preserve consistency when migrating from these different phases? So I'm going to talk about more about those two main points in the next few slides. Okay, so this is the overall architecture of our system. We integrate both hardware and software in the same framework. So again, I'm using NVPhTM for hardware, represented in blue, and PSTM for software, represented in orange here. So let me go step by step to make it clear. So while executing hardware, we use the operating system copy and write support for creating this working snapshot. And the hardware transaction, you should load and store instruction to this working snapshot. So we never ever change persistent memory directly. You only change this working snapshot. And when the transaction is finally committed, it creates a redo log and persists it in this log area in persistent memory. So once the redo log is persisted, we say the transaction is durable. When I think about this architecture is that we decouple transaction processing from log replay, because the log replay is done by asynchronous background processes that read these logs, redo logs, and replay them in this persistent memory, this persistent snapshot. So this is nice, allows for more performance, but there might be an issue here, because if the rate that the transactions write to this log area is higher than the checkpoint process can read and process, the system will stall because the log area will become full and the system has eventually to stall. So we want to avoid that. And also I can force the checkpoint processes to replay all the logs by invoking this explicitly. And this is important when migrating from hardware to software, because I want to make sure that the logs are replayed before migrating to the software part. So this is mostly what happens in the hardware part. For the software part, we don't use this copy and write approach. We just read directly from the persistent data, the persistent memory. We also construct a redo log persistent in the log area in persistent memory, and finally replace them afterwards. So the process is a bit more simple than what happens in the hardware part. And the nice thing about this in software is that we don't have this background checkpoint process, therefore we cannot have this log-induced stagnation issue. So this is the overall architecture. So let me go into more details about how do we change from one mode to another, and how do we guarantee consistency when migrating from the different phases. So of course we want to start from the hardware because it's faster. We transition to software when there are a lot of capacity boards, meaning that I cannot execute in hardware. Or we reach that log-induced stagnation issue. That means that the log area is full, but performance in hardware is not great, so it's a better idea to just switch to software. Once in software, we decide to return to hardware when we see that the transaction is short, meaning that we're probably going to execute better in hardware, or we have come to the conclusion that the log stagnation is not an issue anymore. The problem here is that while in software mode, we don't know what's happening in the hardware part. So we came up with an indirect way of measuring that. So this plot shows that I have time in the x-axis, measuring cycle, transaction length in the left side, y-axis, and also the write set size in the y-axis in my right side. So we run the application, this I think is Intruder, and measure the performance using hardware only, which is in this plot represented by this red plot. And then we execute it in software, represented by the blue dots. And also we measure the write set size. We can see that in the very beginning hardware is better because the hardware transactions are generating a lot of redo logs that cannot be replayed very quickly, and the system enters in that log-induced stagnation. But as time passes by, we can see that the write set is decreasing and the hardware transactions eventually get better. So we use this decrease in the write set size to decide to return to hardware. So that's our main heuristics, to decide when to return to hardware once in software. So going back to the transition automaton, there's another phase to deal with serialization. I'll not go much into details, there are more in the paper for those interested. But basically, you have short transactions in a lot of boards. Instead of going to software, I'll enter a serialization phase instead. And once the serial transaction is committed, I return to hardware. Pure concurrent hardware phase. Okay, so that's the main ideas behind the heuristics. This is a simplification. The more details are in the paper. So the last part here is the consolidation strategy. So if a failure occurs while in hardware software, it's simple to resolve. We just replay the redo log. The problem is if a failure occurs during a phase migration, when I'm migrating from hardware to software, software to hardware. So our solution is just to force all the redo logs to be replayed before migrating. So we insert barriers to make sure that happens. And the problem with barriers is that, of course, it adds some overhead. So we want to make sure that this phase migration don't happen very frequently. So when going to hardware to software, just wait for the checkpoint process to replay or redo logs. When going to software to hardware, we wait for our transactions to have finished. So that's the main idea. So let me show you some results to show how efficient the heuristics are. Our methodology is based on simulation environment, like previous work, such as NVPhTM and Crafty. We have 4 systems: a pure hardware NVPhTM, a pure software PSTM, a version of our approach without the NVM-aware heuristics, which we call PHTM star, and our proposal in NVPhTM. Again, I'm not going to show all the results in the paper. I'm going to focus on the most important ones. There are two applications. One is SSA2. Here I have the speedup graph, number of threads in the x-axis and the speedup in the y-axis. If you look only to hardware and software approaches, we can see that for low thread counts, you can see the hardware is slightly better, but once we reach 6 threads, the software starts to become better because of that log-induced stagnation issue. If you look at the system without the heuristics, the PhTM star, we can see that it doesn't really follow the best performing system, which after 6 threads is softer, because it doesn't know that the log-induced stagnation issue is present because it's not being aware. So when we add that heuristic, we can see that our system now closely follows the best performance one. If we look at some data, so I have here a table for the system without the heuristics and with the heuristics. There are 4 columns for each one. We have the percentage of time per hardware, software, serialization mode, the global log, and log-induced stagnation. You can see that the numbers for the log stagnation issue is much lower for our version with the heuristics. So that's why it reaches much better performance. And finally, the intruder. Intruder is a different case. Intruder, all the configurations, the hardware part is better. If you look at the performance of the system without any NVM-aware heuristics, we can see that it's something between software and hardware. It's better than software, but it doesn't reach the full potential that hardware provides. And that because without the heuristics, we don't know when to return to hardware. It kind of spends most of the time, more time than necessary in software. So when we add the heuristic that indirectly measures log-induced stagnation, we can see that our system performs much better. Looking at that table again, we can see that our system, when we look at the percentage of time that is spent in software mode, our system spends much less time in software than the system without the heuristics, meaning that that heuristic that force the migration back to hardware is effective. Okay, great. So just to conclude, as far as we know, this is the first approach that adds durability to a phase-based transaction memory system. There are one other work that focus on hybrid system, but that's for some hardware extension that is not present in any commodity hardware nowadays. Our experimental results show that the new heuristics are effective. And as future work, we intend to also measure the system using real persistent memory, most likely Intel 10C. Okay, that's all. Thank you very much. This is the link for the source code available for those interested. Thank you very much.
Thank you very much for the presentation.
Hello, everybody.
Yes, thank you very much for the presentation. And I have not seen any question from the audience in the Slack channel. I'm not sure if any panelist would like to ask the question directly. If yes, please ask. Nothing. So I have 3 questions. I think 3 most interesting questions that appeared in the reviews. So first, how do you avoid switching back and forth frequently? I could imagine an application that has short phases that alternate between long transactions and short transactions. This will lead to high overhead in NVPhTM. What if new transactions come in while the switch is waiting to happen? So according to the section 3.3, it seems that they will all be blocked, which would add to even higher overhead. So some worst case examples should be used to test the limits of your approach. So this is one of the questions, and please, can you?
Okay, thank you very much. Thank you very much for the question. So can you hear me?
Yes.
Just to make sure that, okay, great. So that's a very good question, and it's one of the questions that is always asked. So the thing is, if you look at the original phase-based systems, they had a lot of these migrations. So one of the things we did is that we kind of limit these frequent transitions by staying a certain time when migrating. So for instance, when you go from hardware to software, you have a time frame that you use to reevaluate if you need to return or not to hardware. So by doing that, we kind of avoid switching back and forth much of the time. And there are also some more optimizations that are not explicit in the paper that used to avoid those kind of things. But you are right that if you migrate all of the time, the performance is not very good because you have overhead when migrating, because you have a barrier. That means that you need to wait for all the transactions to finish one mode before migrating to the other. So we basically, to sum it up, we have these time frames that we use to avoid switching back and forth all the time.
Okay, thank you. And I think we still have time for another question. So the log, there is a question from the audience. Yes, so please, this topic is clearly of considerable practical and industrial application impact. What are the steps needed from here to get to a software product that someone could really use for a business critical purpose?
Oh, that's a very hard question to answer. Yeah, so one of the things that, I think the whole transactional memory community is always questioning is that we don't have, we have a few benchmarks. So all of this work that we have done is based on stamp benchmark. And for our system to work, you need to have applications that have different phases. But one of the things that we notice is that for this stamp benchmark, which is the main benchmark used for transactional memory in general, the applications, they don't display this behavior, this phase behavior. So most of the time they stay in just one phase. If you look at the hybrid transactional memory approaches, they also don't have that much performance gains because the applications only have mostly a single phase. So I think the first point is to find good applications that display that behavior, and unfortunately we don't have that right now. I think there's a paper we published last year that comments on that particular issue. So I think we need better benchmarks and then start thinking about that.
Okay, thank you. Thank you. We have finished your time slot, so we have to move on to the next.
Thank you very much.
Thank you very much, and maybe you can continue discussion in the Slack.
Sure.
And then we move to another presentation.